Hi everyone, my name is Hamed Gorgiara from UC Irvine, and today I'll be presenting Satune, a tool for synthesizing efficient SAT encoders. This is a joint work with Hari Zhu from UCLA and Brian Dembski from UC Irvine. Modern software analysis from planner frameworks to hardware-software verifiers rely heavily on constraint solving for the reasoning or search task. Developers of these tools usually have two options to solve these constraint problems. They can either develop their own custom solver, which is labor intensive and often not efficient, or they can use general purpose constraint solvers such as SMT or SAT solvers that have been carefully engineered over 50 years of research and are usually faster than the former option. To use most SAT solvers, the original problem has to be encoded as conjunctive normal form or CNF by the encoder component in the tool. After finding the solution, the encoder component needs to translate it back to the original problem domain. The process of encoding is not straightforward, and there are many different encoding strategies that the encoder component can use, but not all of them yield good performance. We did an experiment on a randomly generated total order constraints for different encodings. As you can see, the solving time for the encoding marked as green is less than a second, and for the encoding marked as red is more than 15 minutes. So the same problem with the same SAT solver, but different encodings can yield performance results that are orders of magnitude apart. Finding a good encoding is very difficult, and the developers of constraint-based tools can face different challenges. For example, there are many different encodings, and trying all of them is labor-intensive and time-consuming. Furthermore, the developers need to have a deep knowledge about details of SAT solvers and how different encodings interact with each other to choose the right encodings for their tools. Also, some encodings might work well for easy problems. However, when the formula grows, those encodings may not have good performance. Moreover, encodings are domain specific, and one encoding can be the best in one domain, but it may perform poorly in other domains. There is a lot of work on analyzing and optimizing the SAT formula, such as extracting features to select the best SAT solver or tune the SAT solver. There are also works that find the commonly used patterns in the formula and try to rewrite and optimize those patterns. And lastly, there are tools that auto-tune a set of rewrite candidates. All the previous works assume that the encoding of the problem domain into a formula is done by the user. We hypothesize that instead of optimizing the encoded formula, if we tune the entire encoding process, we can get a better performance improvement. The manual process of encoding is to gather a set of problems, guess one encoding, implement and evaluate it, and keep repeating the process until we find a good encoding for our tool. Usually, people will stop before getting the optimal result. Our insight is that since the encodings are domain specific, we can use a small set of problems to find near optimal encodings for the entire domain. Based on this insight, we developed a tool called Satune to automate and optimize this encoding process. Satune provides a high-level language that gives the tool this flexibility to support different encodings. It also has a pipeline of different optimizations and encodings, but not all these optimizations are beneficial for all problems in different domains. So these optimizations and these encodings are being controlled and tuned by the tuner framework. Satune Domain-Specific Language, or DSL, supports three widely used abstractions: total or partial order constraint over a discrete set, integer variables drawn from a discrete set, and Boolean abstraction. The language also supports labeling different use cases because potentially different use cases can benefit from different encodings. No existing languages could be used because of the lack of support for labeling variables and representing order constraints. Once the problem is encoded in Satune's DSL, Satune optionally runs many optimizations to simplify the problem as much as possible. That causes Satune to select simpler encodings and potentially activate further optimizations. Satune benefits from existing optimizations such as pure literal elimination and order conversion, as well as integer domain reduction and our novel order optimization. For certain domains, it can be extremely important to simplify order constraint as much as possible, since complexity of the encoding grows superlinearly with the size of the order set. Satune implements optional order optimizations that benefit from knowing the Polarity of order variables. The polarity of an order variable is positive if the variable appears with an even number of negations, otherwise it would be negative. Polarity is important since a variable that appears only in the positive polarity only can contribute to satisfying the entire formula if it is true. Satune builds an order graph and uses polarity analysis and different optimizations to simplify it. For each item in the order set, there is a vertex in the graph. If an order variable x1 and x2 is used in positive polarity, or order variable x2 and x1 is used in negative polarity, we will add the corresponding edge from vertex x1 to x2. This edge shows x1 may be ordered before x2. If Saturn determines that, for example, x4 must be ordered before x5, it marks the edge from x4 to x5 as must be true, which is shown in red in the graph. After adding edges for all order variables in the constraint, the order graph is built and Saturn can optimize it. The first optional optimization is transitive must be true, which traverses the graph and adds order implied by transitivity. In our example, x3 ordered before x5, x5 ordered before x6, so it can be inferred that x3 ordered before x6. Same reasoning for x4. The next optional optimization is called vertex elimination. The idea is that if there is a node where all incoming edges and all outgoing edges are true, that node can be safely removed and the corresponding edges can be added. X5 matches this property and it is removed from the graph. Another optional analysis is called must-edge pruning. If there is an edge that is marked to be true, and either its destination has no other incoming edges, or its source has no other outgoing edges, the source and the destination of that edge can be safely merged. Both x3 and x4 have the latter property, and they both can be merged with x6. Lastly, Satune can optionally enable order decompose optimization. The core idea is to run a strongly connected component or SEC analysis on the order graph, and the edges between SECs can be considered to be true and be removed from the graph. As a result of all these optimizations, the initial order example with 7 items is reduced to 2 simpler order constraints with 2 items. I presented the case for total orders, but Satune implements a variation of these analyses for partial orders also. After simplifying the problem by different optimizations, Satune assigns encoding to variables, and optionally, it can encode variables by using graph-based encoder. The main idea is that for any variable x and y that can be encoded by using binary index and participated in any equality and inequality constraints, instead of just enumerating all possibilities, variables can be encoded by bitwise comparison, which is simpler. This type of encoding is called circuit-based encoding. But the question is that what are the necessary conditions for using circuit-based encodings? It is safe to use this encoding for x equal to y if both x and y encode all shared values in the same way and do not use the same encoding for different values. Also, it is possible to use circuit-based encoding for inequalities if x and y assign encodings in a way to preserve the order of values. Based on these 3 properties, we developed a novel graph-based encoding. I walked through the algorithm with an example, but the encoding can be extended to any example with any level of difficulty. Here, we have 4 sets w, x, y, z, and 3 constraints of w less than x, x equal to y, and y equal to z. The dots shows other constraints that don't matter for this example. For the given problem, we first need to build a constraint subgraph. For each set, there will be a vertex in the graph. For each equality and inequality between 2 integer variables, we add the corresponding edge between the sets that these 2 variables are drawn from. For example, for w less than x, we add an inequality edge between vertex x and vertex w. Once the constraint subgraph is built, we can convert it to the encoding graph. In order to do that, we split each node into the values that the node contains and add the corresponding edges between new nodes. For instance, set W has 2 values, so vertex W splits into 2. In the encoding graph, inequality edges must be directed toward the larger values. Then Satune merges the node with the same value that are connected. So they all get the same encoding. For example, zeros are connected and they all will be merged. First, Satune assigns encodings to the vertices that appeared in inequalities, which are marked as red. We topologically sort the red graph to assign unique encodings to the node in a topological order. The node 0 has no incoming edges, gets encoding binary 0, and the next node gets the next numbers. Then Satune assigns encodings to the vertices that participated only in equality constraint by using a greedy graph coloring algorithm. It starts from the node with the largest number of neighbors and assign unique encodings to the nodes one by one in decreasing order. Now all the encodings are assigned to values, and as you can see, the same values from different sets that are compared have the same encoding, and we can use circuit-based encoding to encode the constraints. After graph-based encoding, if there are still variables that have no encodings, the tuner framework assigns encodings to them. After an optimization, the problem is encoded into CNF and it is passed to a SAT solver. Once the problem is solved, the Boolean result is translated back to the client. So there is a huge number of knobs to control different optimizations, encodings, and heuristics, and we want to find a good setting for all these knobs. How do we do that? By using our tuner framework that has three primary components. First, language support that allows clients to tag variables in different use cases. Second, integrating with optimizations and encodings to enable, disable, and tune them for a specific domain. And lastly, implementing a variation of simulated annealing algorithm to explore the search space efficiently to find good encoders. The original simulated annealing algorithm works as follows. At each step, an encoder close to the current encoder is selected, and based on their performance, algorithm decides to keep them for the next iteration. In order to avoid getting caught at local maxima, the algorithm accepts bad encoders only at the beginning of the search. For some problem domains, it can be beneficial to use different encoders in parallel and take the result from the encoder that finishes first. Using the standard algorithm to produce multiple encoders would generate a set of potentially identical encoders that work well for the problem set. However, the goal of tuner framework is to find multiple different encoders that are complementary, and the combination of them yield the best performance. So the tuner framework implements a weighted scoring algorithm that gives points based on how good an encoder is relative to others. In the example, encoder 5 was the faster for problem A and got the maximum score. At each iteration of the algorithm, Satune sums the scores for all problems for each encoder and picks the best n encoders for either the next iteration or giving them to the client if the budget is finished. In the example, encoder 5, 10, and 3 will be picked. Okay, we evaluated Satune on 3 real-world benchmarks and 3 puzzles. Dirk and JMCR use Z3, and Sciped uses Sat4j, and all puzzle games use Glucose as their constraint solvers. We use popular n-fold cross-validation to learn encodings for each benchmark. On average, we could get 10 times performance improvement compared to the baseline for all the benchmarks. The first benchmark is JMCR, which is a stateless model checker that implements maximal causality reduction algorithm. It uses order constraint to generate new executions. We use 4-fold cross-validation on 4 test cases. In this figure, the y-axis represents time in logarithmic scale, and x-axis is the name of the test cases. Satune's test results are shown in purple in the base, and the baseline is in the green. In this figure, the lower is the better, and as you can see, Satune was faster than the baseline in all the test cases. The next benchmark is Sciped. Sciped is a type-directed tool for API synthesis. It uses integer variables for each function signature. We use 4-fold cross-validation over 4 test cases. Again, we are reporting the same figure for Sciped, and as you can see, Satune was faster than the baseline in all the test cases. The next benchmark is Dirk, which is a deadlock and data race predictor. It uses ordering constraint to represent happens before between lock events. We use 2-fold cross-validation for 9 test cases. Again, same figure is reported for Dirk, and as you can see, Satune was faster than the baseline in all the test cases. To conclude, Discovering a good SAT encoding for a problem domain is difficult, and current approaches only focus on optimizing the encoded formula. As a solution, we presented Satune, a tool that incorporates a collection of encodings and optimizations and automatically finds the best domain-specific encodings. Evaluating Satune over 6 benchmarks showed an average of 10 times performance improvement compared to the original encoding. Satune is now available on our website for public usage. Thank you.